Let's take a look at the solutions to the assessment on the ratio test. In the first problem, which had several parts, we're asked to use the ratio test to determine if a series converges or diverges. And so the first thing we need to do for this is set up a ratio, and we're going to take the limit as n approaches infinity of the n plus first term on top over the nth term on the bottom. Now, it's important for the ratio test to work that these terms are going to be positive. N to any power, since n is starting at 0 and going to infinity, n to any power is going to be positive, and 10 to the nth power is also going to be positive, so we don't have to worry about absolute series here. These are going to be positive terms. To simplify this, we will multiply by the reciprocal of the denominator, and we'll see here that the 10 to the n is going to cancel out with 10 to the n in the bottom, and so we're left with just 10 down there. And since that 10 doesn't have anything to do with the n, it's independent of the n, we can rewrite this limit as 1/10 times the limit as n approaches infinity of n plus 1 to the 10th over n to the 10th. Now, there's several ways that we could evaluate this limit. We could use L'Hopital's rule, or we could rewrite this algebraically. I like doing the latter. If we rewrite it as such, 1 plus 1 over n to the 10th, then we can see that as n approaches infinity, this term here will approach 0, and so we have 1 plus 0 to the 10th, which is going to be 1. So our limit is going to end up being 1/10. Now, according to the ratio test, if this limit is less than 1, as this one is here, then the series is going to converge due to the ratio test. In this problem, points were given for the answer that the series converges. This answer is dependent on having this inequality written, though. You can get the point for the answer if you have 1/10. You don't have to have the inequality written, but you also get another point for the inequality, and then another point for setting up the limit of the ratios of the n plus first term to the nth term. In part B, same thing, we set up the ratio n plus first term over the nth term. Again, we have all positive terms, so we don't need to worry about absolute values here. Rewrite it as multiplying by the reciprocal. Cancel out what we can. This 2 here that we have left in the numerator is independent of n, so we get 2 times the limit as n approaches infinity of n plus 1 over n plus 2, and that is going to approach 1. Again, we could evaluate this limit in a variety of ways. L'Hopital's rule would be a good one, or if we multiply the top and the bottom by 1 over n, we'll write it in a fashion that we can evaluate it. Either way, we end up getting 2 for the limit of the ratios, and since that is greater than 1, according to the ratio test, the series is going to diverge. And so in this problem, points were given for the final answer, that it diverges. A point was given for the setup, for the limit of the ratio of terms, and then also for the inequality. In part C, we do the same thing. Again, we have all positive terms here. So we simplify the ratio by multiplying by the reciprocal. And this time it's going to simplify in 2 ways. The e to the n plus 1 and the e to the n will simplify, but also the n factorial and the n plus 1 factorial will simplify. Since n plus 1 factorial is just n plus 1 times n factorial, then we end up with this. As n approaches infinity here, then we're going to have 1 over e times infinity, which is infinity, clearly greater than 1. So according to the ratio test, this series will diverge. In this problem, points were given in the same way for the final answer, for the setup of the limit of the ratios, or the ratio, and then also the inequality. And for part D, same thing, we set up our limit. This one also involves factorials. Factorials cancel nicely in these ratios, and so we end up with 2 times the limit as n approaches infinity of 1 over n plus 1, which is going to be 0, so we get 2 times 0. And since 0 is less than 1, this series will converge due to the ratio test. Points were given again for the answer of a converging series, for the setup, and then also for the inequality. In the second problem, we're asked to use the ratio test to determine the interval of convergence. Using the ratio test, we can only find the interval of convergence excluding the endpoints. We don't know, according to the ratio test, what's happening at the endpoints because those endpoints are going to be when the limit is equal to 1. And keep in mind that the ratio test is inconclusive when the ratio equals 1. So we're going to set this up the same way. And what we're looking for here is a range of x values that we know will converge. So we set up the limit of the ratios of the n plus first term to the nth term. We multiply by the reciprocal. In this particular problem, it's important to have the absolute values here because if x were certain numbers, anything less than 2/3 in fact, then this is going to be negative, and for the ratio test to work it has to be all absolute value, or it has to be all positive terms. So what we're going to end up finding here is when the series converges absolutely. And we know if the series converges absolutely, it also converges. So we multiply by the reciprocal. We rewrite it. Since the absolute value of 3x minus 2 is independent of n, we can rewrite it outside of the limit. And so we have the limit of n over n plus 1 as n approaches infinity. And we could, again, use L'Hopital's rule or some algebraic manipulation to find that this limit is 1. And so this series is going to converge when this limit is less than 1. So we rewrite this without the absolute values, and it would look like this. -1 is less than 3x plus 2 is less than 1. And solving that, we get -1 is less than x is less than -1/3. Or we could write it in interval notation like this. Again, we're going to leave it as an open interval for now because we don't know what happens when x equals -1 and when x equals -1/3. At those points, the ratio test would be inconclusive because the ratio would equal 1. Points were given on this one for the final answer of the interval. For the setup, the limit of the ratio of the n plus first term to the nth term, and then also for the inequality, showing that the absolute value of 3x plus 2 is less than 1. And finally, in the last part, this is very similar to part A in question number 2. Again, since x could be any value, we have to make sure that we take the absolute value of x. Since these have to be positive, we don't need to worry about absolute values on the 2n plus 5 and the 2n plus 3 because that always has to be positive as n starts at 0 and goes up from there. We'll rewrite this by multiplying by the reciprocal. We'll cancel what we can. In this case, when the exponents cancel, we end up with absolute value of x squared on top because the exponent in the numerator was 2 bigger than the exponent in the denominator. So we end up with x squared times the limit as n approaches infinity of 2n plus 3 over 2n plus 5. We're able to drop the absolute values here because regardless of whether x is positive or negative, if we were to square it, it would be positive. And so the absolute value here is not necessary. We could use L'Hopital's rule or algebraic manipulation to show this limit is going to be 1. And so our ratio, the limit of our ratio is going to be x squared. So then we need to figure out when x squared is going to be less than 1, and that's going to be true when x is between -1 and 1. So we could write it either like this as an inequality, or we could write it in interval notation. 3 points again for this problem, 1 for the final answer, 1 for the setup, and 1 for the inequality right here.